Okay, so let's continue, and I'm going to give you a couple practice problems. So practice. And yeah, so the first one, identifying open intervals. Where a function is decreasing and increasing. Increasing / decreasing. Okay, and the function looks like this. So we have x squared minus 2x minus 8. Okay, so that's the first problem. The second problem. Okay, basically it's similar, right? But I also would like you to find those maxima and minima. So we have 2x cubed plus 3x squared. And then minus 12x. Okay, and yeah, what I'd like you to do is find the intervals. There's, increasing, decreasing. So find where the function is increasing, where it's decreasing, intervals. And then locate. Let me write it maybe like this. Use the first derivative test. To find local maxima and minima, local extrema. Okay, so we have that. Let me see. Yeah, so that's these are the problems, just two. Let me give you the answers. So the first one, so decreasing. I have that from negative infinity to 1. Right, so that critical number is 1. And then increasing, can I squeeze it in here somewhere? Maybe if I did this. So that was decreasing, increasing. Let me just double check. Yeah, decreasing. So increasing. So that's from 1 to infinity. And then the second one, so increasing. We have increasing on from negative infinity to negative 2. That's the first interval. The second one is from 1 to infinity. Okay, and then decreasing. Okay, so that interval is from negative 2 to 1. Okay, and then we have local maximum. That's at negative 220. And then minimum from 1 to negative 7. Okay, so these are the answers, and yeah, what else do we need to do? All right. Yeah, so I have another example, maybe slightly more difficult. So example, what is example 4? I'm not sure about this, how this is right. So we need to analyze. So basically that means, right, figure out those those intervals, function decreasing, increasing, and also that minimum, maximum. So what do we need to analyze is, okay, function that looks like this of f of x. So we have x squared minus 4, and then it's to the power of 2/3. And yeah, we also know that the function is continuous. Okay, yeah, maybe you could try to do this by yourself and then check. So yeah, you can pause video and try to do it on your own. Anyway, so we start by taking the first derivative, so f prime of x, and then this example kind of, right, gives you a chance to practice the chain rule. Right, chain rule was right, one of the differentiation techniques where you figure out derivative of a function that's a composition of two functions, right? So we have two functions going on here. So the first one is that this is my outside function, right, 2/3, and this is the inside function. So the way chain rule works is that you take a derivative of the outside, right? So that when I'm taking that 2/3, right, putting it to the front, subtracting 1, and then multiplying by the derivative of the inside. Okay, so it goes like this. So 2/3, I keep that inside function unchanged. 4, let me erase this continuous. And then I multiply it by the derivative of the inside, right? Derivative of the inside is 2x. Something's missing, right? So I still need to, I forgot about this, right? So minus 1. So that will be negative 1/3. Negative 1/3. And let me rewrite it in just like a rational form. So we'll have, so I have on the top, right? By rational form, I mean a fraction, right? Because this, right, negative 1/3 will take this parenthesis, right? Because this negative 1/3 only applies to that parenthesis. It's going to push it down to the denominator, right? So in the denominator I have x squared minus 4. And then that negative is spent, so this is 1/3. Right, so this is cubic root of also. And then, right, then 2/3 doesn't go anywhere, so I have 3. 2, then I have 2 times 2, 4. So 4x on the top. Okay, and we need to figure out, we need to make it equal to 0. And now solve it. So if we solve it for x, you're simply going to get x equals 0, because the only way to make it 0 is by plugging in 0 here. So x is 0. But keep in mind that critical numbers were also numbers that where the derivative doesn't exist, where the derivative is not defined. Right? So those types of critical numbers come from the usually denominator. Okay, so in our case, we have two numbers that would make denominator equal to 0, and those numbers are x equals 2, And because we can factor that x squared minus 4, so x equals 2, and then x equals negative 2. And so we have 3 critical numbers. And yeah, the next thing, we put them on the number line and see what's going on. Okay, number line. And we have, what do we have? Negative 2. Critical numbers were what? I think blue. Okay, so negative 2, 0, and 2. And then we pick couple, what do you call them? Testing numbers. I'm not sure if that is an official name, testing intervals. So convenient number between negative 2 and 0 would be negative 1, right? And then convenient number here will be 1. And over here, I'll pick 3. Alright, so as I said, those testing numbers, right, those red numbers, are just picked completely arbitrarily, right? I'm trying to find numbers that are easy to evaluate my derivative for. Okay, so yeah, you guys can do. Maybe I'll show you a couple of those examples, right? So I'm taking the negative 3, right? I'm starting with this and putting it here, right, in those two places, and trying to figure out what this sign will be. So let's do f of negative 3. And yeah, I'm just taking that negative 3 and just plugging it first in the numerator, right? So I'm going to get negative sign in the numerator. So negative. Write it again. Okay, so negative here. And then denominator, right? So we have, I'm plugging in negative 3 here. So negative 3 squared would be 9 minus 4. And then, right, we do the arithmetic and we get a positive number here. Right, 9 minus 4, and then the rest is positive. So this will be positive. All right, so finally I will get negative. Okay, so negative, I believe was yellow. Okay, so negative over here. So the function goes down, right? So decreasing function in that interval between negative infinity and negative 2. Okay, so let's keep going. Right, so next thing I have is negative 1, right? So I'm taking this and plugging into the derivative. Yes, it's derivative, right? So it's not f, it's f prime. So f prime of negative 1. Right, and again, it's the same thought process, right? So I'm taking the negative 1, plugging it into the numerator, so that's gonna be negative. At 4 times negative 1 is still negative. And now denominator, I believe, is going to be negative just by looking at it, right? So negative 1 here, so negative 1 squared. So that's going to be negative. Cube root of negative, still negative, times 3 negative. All right, so I have negative. And the whole thing will be positive. All right, and then we keep going. So we have f prime. The next testing number is 1. All right, so the top will be positive, and the bottom negative. Okay, so we get negative. Okay, and the last one was f of 3, f prime of 3. Okay, so the top is positive, and the bottom, right? Again, I'm looking here. So I'm plugging in 3, so 9 minus 4, positive. Alright, so this was positive, the whole thing is positive. Okay, so let's put it here on the number line. Okay, so between numbers, so interval between -2 and 0, I was plugging in -1. Right, so I'm plugging in -1. So that was give me a positive. Right, so you see that it usually it alternates between positive and negative, but not always. So this will be increasing. And then I remember the next interval, right, I was checking for 1. I'm looking at this here. Right, 1. So the next interval was negative. Okay, so negative over here, and then the last interval was again positive, so plus, and okay, looks like this. And at this point, you don't have to do that, but it's kind of good to draw those the shape of those functions, right? So the shape of the graph at those critical numbers. So you see, right? So this looks like this. Okay, so I'll have local minimum. Here I have this, so local maximum. And here again, right? It's like this. So local minimum. Okay. Yeah, so what else do we need to do? It'd be good to look at the graph and then maybe write down the solution, the answer. Okay, so let's look at the graph. Okay, so the graph looks like this. Okay, so critical numbers. So that was -2. Then we had 2. And then the last one was 0. So it's here. And the graph looks like this. Kind of here and then goes up. And we have that local maximum down and over here. Okay, so yeah, so let me color code it, right? So that was decreasing, and we had 2 intervals for decreasing and 2 intervals for increasing. Okay, so let's write it down. So increasing. Let me just to save time, right? So increasing would be this. So we have from -2 to 0. And then the other one is from 2 to positive infinity. Okay, and then decreasing. So that would be from negative infinity to -2. And then the other one is from 0 to 2. Okay, let me just confirm it with that number line. Right? So the first between negative infinity to -2 was decreasing. Okay, and then we had decreasing from 0 to 2. From 0 to 2. Okay, that works. And then local maximum, local minimum. So maximum at 0, and then we can figure out that number, maybe. I'm not sure. And what that y value is. So where is the original function? Okay, so we're doing f of 0. Okay, let me do it here on the side. F of 0. Right, so the function was, I need more space, I think. F of 0. The function looked like, let me see it in my notes, x squared minus 4. Actually put that 0 there. So 0 minus 4, 0 squared minus 4, and then to the power of 2/3. I see that it's not going to be easy to figure out that number. Anyway, so we have, what do we have? We have negative 4. Raise it to the second power, so we have 16. So we have cube root of 16. Okay, so that's gonna be 2 times cube root of 2. Okay, right, so you see that 16 is 2 times 2, we can take a cube root of 8. 16 is 2 times 8, so cube root of 8 is 2, so I pulled it out. Okay, that's here. And then cube root of 2, I'm not sure what that is. So that number, right, I'm not going to give you the right answer, so it's about, I don't know, 2 times 1.1, I don't know, 2.5. You guys can figure it out, right? Use a calculator. Okay, so that's my estimate. I hope it's close. I'm going to leave this blank. You can fill it out. So that was the maximum, and we had 2 minima, right? So we had minimum at negative 2 and positive 2, right? I'm looking at this part here and this part. So we had minima at so we had negative 2, 0. And 2, 0. Okay, so that's right. That's easy to figure out with those y's. Just plug in negative 2 and positive 2, and you get 0. Okay, yeah. So that's that basically. Oh, yeah. There is one more result that I want to talk about. Okay, so I want to talk about mean value theorem. It's another important result. Let me organize my things here. Okay, mean value theorem. Mean. This is mean, right? Mean meaning average, and it goes like this. So let f of x be so it's a continuous and be continuous and differentiable function. Function on a specific interval, so on AB. Okay, so there is at least one number C. At least one in that interval. Such that f prime of C basically and that the slope of the function at that number is the same as the slope of the line that connects those 2 points. I'll show it to you on the graph. So b minus a. And then I'll write a little simplified version of this theorem. But basically, right, so if you have some curve, some function, right, so something like this, and this is point A, this is point B, so A, B, okay, B. What's the easiest way to fix this? Maybe like this, by extending the x-axis. Okay, so my B is here. Now if I draw a secant line that connects those 2 points, okay, let me okay, I succeeded. Right, so the theorem states that, before I'll explain it, let me so this point has coordinates b, f of b, right, f of b. So you see that what I wrote here, and this is the slope, right, of that red line. Okay, so that's gonna be bf of b, and this point has coordinates a, f of a, right? Right, so these 2 points, this point, then we have a line, secant line that connects those 2 points, and then the theorem says if there is right, that in that interval there is another point, another number, c, and if I draw a tangent line to the curve at that point, and those 2 slopes will be the same. Okay, so that's what this says. Right, so derivative of the function at that point c will be the same, right? So this slope, right, so that's this, will be the same as this slope, right? So there is at least one point on that curve like that. So that's what that theorem says. Okay, yeah, let's do an example. So I'll do one example and then I'll give you one problem to practice. So example 6, that's what I have. We have verify mean value theorem. This is T. Okay, so we have a function and then specific interval, right? So the function is 5. Okay, so 5 minus 4 over 6. Sorry, 5 minus 4 over x. And let me rewrite it here. So it's 5 minus 4 times x to the negative first power, right? So, and then interval we're given here is from 1 to 4. Okay, so yeah, so let's start by finding the slope between those 2 points, just given that interval. Okay, so maybe let me write what we're doing. So slope between 2 endpoints. All right, so so we have some. I'm just going to sketch it just to explain what's going on. Right, so we have some curve. We don't know what that is. So this is 1. This is 4. We don't know yet what what the y values for those 2 numbers are. And then, right, we have that secant line connecting those 2 points, and we're figuring out the slope of that red line. Okay, so that's the idea. And then we'll take a derivative and we'll plug in the number that we found here. All right, so let's figure out that slope. Okay, so I'm going to write AB, and it will be f of b. And this is just a regular formula for slope, right? So it's y2 minus y1, and then x2 minus x1, right? So, well, yeah, this is not x, this is a. Okay, so we have that, and now we just need to figure out that f of b and f of a. Okay, so for f of b I have 4, so I'm taking, right, so let me show you quickly what we're doing, right? So we're doing this, plugging this in here, so 4 over 4, 1, 5 minus 1, so that's 4, so f of b is 4. Now f of 1, so I'm taking 1, right, 1, plugging it into the function, figure out what that value is, y value, right? So that's 1, because I have 5 minus 4. And then the bottom is just the x's, right? So it's 4 minus 1. Same, right? Okay, so if we do the arithmetic, 3 over 3, so that slope is 1. Okay. Okay, so next thing we'll figure out what derivative is, so f prime of x. Okay, so you guys can do that derivative. Right, so I'm taking derivative of this, right, of my original function, this or this, and what I have is 4 over x squared. Okay, so I'm looking for x that would give me that slope of 1, right? And I need to confirm that such an x exists, right? So I'm solving this equation. Okay, let me write it. Maybe on the next page. Okay, so we have 4 over x squared. X squared equals 1. Okay, so we can solve it, multiply both sides by x squared, or think about it. What numbers do I put in for x to get 1? So those two numbers are negative 2 and 2. Okay, so you see that second number, right? This number is not in our interval, right? So that interval was from 1 to 4, and we were interested in. Okay, and that second number is not in that interval, right? So this one. So we're just kind of cross it out. Okay, so that number is c, right? So c is equal to. Okay, so that's for that. If I evaluate my function, the derivative for that will give me the slope of 1, right? So if I have, right, so we have that f prime, where we are, we're here, where are we? Right, so f prime of 2. Right, so f prime, so that's, I'm going to write it maybe using x. Right, so this is the formula for slope, right, of that particular curve at that particular point, right? We plug it in, well, for any point on that curve, right? So anyway, so we have 2 squared. Right, so we have 1, and that's the slope, right, of the curve at point 2, right? And that slope is the same as the slope of the line connecting those 2 points. Let me graph it. Okay. All right, so we have some curve. We don't really know what that curve looks like, but the interval we're interested in is from 1 to 4. Okay, so let's calculate quickly let's say if this is 1, then if I plug in that 1, actually we already know. I did it somewhere before. Oh yeah, so it's 1 1 and 4 4, right? So we did it here. We evaluated, we found the y's, right? So over here, oops, I don't know how to undo it, too late now. We evaluated so there was f of b minus f of a. It was easier than I thought to redo it. Anyway, right, so evaluated, we found the y values, right, for those two, for 1 and 4, so they're here. So we know what those points are. So the first point was 1 1, and the second point was 4 4. Okay, so now that is the curve. And now for 2, let me draw that. Alright, so that's the line connecting, secant line connecting those points. So m was 1. And then we found number, that was number 2, that's c. It's over here, where that slope is the same. Slope of the tangent line to the curve at that point. So m equals also 1. And so that's how that mean value theorem works. Okay, so yeah, so that was an example. Let me give you a problem. So problem. Yeah, so just one problem. So verify mean value theorem. For f of x equals sine of x. So sine x. And the interval we have is from 0 to pi. Okay. Yeah, so I hope you guys can figure it out. Let me give you the solution. So the slope m is equal to 0, and it happens at, let's see, right? So that's the slope between, well, obviously, I don't want to give you, right, give you the answer, but right, obviously the slope is 0, right, on those, for sine x, for those 2 points. Anyway, and it occurs at pi over 2. Okay. Yeah, so figure it out. Show work, show what you're doing. And that's it for that 4.2.